So our today's lecture will be devoted to a certain very useful method to solve linear differential equations, certain class of them with linear coefficients. And in order to get some understanding and to provide you with introduction to this method, let us recall Airy's equation, which is well familiar to us by now. And again, as usual, it will provide us with the primitive example of our new technique. So, and this equation is conveniently solved with the use of Fourier transformation. So we introduce new function y capital of p, and this equation can be transformed in the momentum domain by usual rules, where second derivative is replaced by minus p squared, and x is replaced by I d over dp. So as a result, the equation for y small in the x domain becomes the equation for y capital in the momentum domain, which reads as follows. And this equation is to a certain extent much more simple, first of all because it's of the first order, and in fact can be explicitly integrated with the result for y as a function of p equal to exponent of I p cube over 3. Yes. So with this in mind, we can write an expression for obviously only one of particular solutions of this equation, but nevertheless it can be quite useful. So it's 1 over 2 pi for normalization and exponent of I p x plus p cube over 3. In fact, this procedure yields precisely the Airy equation. So the side comment, the normalization here just gives us exactly canonical definition for the Airy function. And now, as it stands, this equation is very useful and allows us to extract a lot of information about this particular solution. But immediate question to be asked is, what about the second linearly independent solution? And in fact, it happens that in order to construct the second linear independent solution, it is necessary to go to the integration in complex P. And let us now develop some procedure which will be quite general and will allow us to solve a wide class of differential equations. And this class can be parameterized in the following form. So this is the most general notation for arbitrary equation in this class. And note that it includes arbitrary derivative of y with respect to independent variable x. And in front of each of the derivative, there is a certain linear function of x. And of course, Airy equation, which we have just considered, is one of the equations of this class. In order to see it more explicitly, note that we can write it first of all like that, which of course is reduced to this class by the following choice of indices: a2 equal to 1 and b0 equal to -1, with all remaining coefficient just identically 0. And we will actually construct this method for some less general case, and we'll consider the following example, in which we will deal with the second order differential equation. But this method by construction will be easily generalizable to a wider class, and it will be obvious for you almost immediately. But before such a generalization, let us consider this equation and construct all linearly independent solutions of it. So let's start.